and welcome to part 2 of our week 7 lecture series, where we have already talked about series circuits. Now we're going to talk about parallel circuits. Now, how do you know something's in parallel? Well, you know something is in parallel because unlike series circuits that share the same current, parallel circuits share the same voltage. And because they share the voltage, they divide the current. In fact, we now apply the third law of Maxwell's equations, and that is Kirchoff's current law. And Kirchoff's current law basically says the sum of the current at any point is equal to 0. So you note that I1, I2, I3, and I4 are all going into this point. And the total current is going out. So therefore, all of those have to sum up to 0, or some people like to say, oh, hey, just add up those going in, and they equal those going out. Now, series circuits are what we see in Christmas tree lights. When one bulb goes out, all of them go out, because when one bulb goes out, the resistance becomes very high. Now, in a parallel circuit, because we have multiple paths for the current to flow, then it is preferable so that if one circuit goes out or one path goes out, you can still provide current to the rest of them. And that's such that if your car, one of the headlights goes out, it doesn't take all the electric out on the entire vehicle. If it was in series, it would do so. And by the way, the original automobiles actually did have their lights and electronics in series. And now, of course, they have them in parallel. Now, because the voltage is shared with everything in parallel, the formula for calculating the total resistance seen by the voltage source is a little on the ugly side. Basically, you take 1 over, so that's 1 divided by, and a parenthesis here, 1 over R1 plus 1 over R2 plus 1 over R3, and all the way down until the very last one. Now, when it comes to total resistance, if you have several like resistors in parallel, you can simply take the value that they are and divide it by how many there are, and that will be the total resistance seen by the source. Now, of course, this is what happens when you overload a circuit. Each load or resistor that you put on to the same outlet basically lowers the resistance. And remember, from Ohm's law, when the resistance overall is lowered, the current will be higher, and because of that, it can cause problems. Now, an alternative formula that can be used, but I caution you on using this last formula. It should only be used when you are only combining 2 resistors at the same time. And that you can take R1 times R2 divided by R1 plus R2. Now, the problem with using this one, if you have 10 resistors, you have to go and only combine them 2 at a time, which can be problematic. Now, if you have 4 resistors that are all valued at 1 k ohm in parallel, what is the total resistance? Well, we take 1.2K, divide it by 400, and it's now 300 ohms. Note, with the more additional resistors that you add in a series circuit, it increases the resistance. In a parallel circuit, the more resistors you add decreases the overall resistance. And so when the current decreases, when the resistance decreases, the current increases. Now, if I had 5 resistors, a 1K, a 4K, a 1K, and a 4K, and a 400 ohms, what would be the total resistance? Well, I could combine just R1 and 3 together to come up with 500, and R2 and 4 to come up with 2K, and then I could say, okay, 500 times 1K divided by 500 plus 2K gives us 400 ohms, and then say 400 ohms divided by 2 gives us 200 ohms, since they're like values. Or I could just simply do it like this, and I'm going to bring my calculator over to show you how to put this one in. The most critical thing when entering this information in with your calculator is you mustn't forget to put in 1 divided by and a parenthesis here, as well as you must refer to each resistor in its appropriate metric prefix. So our first resistor is a 1K ohm, so I do 1 second EE to the third, and I need to go back on that because I need to do 1 divided by 1 second EE to the third plus 1 divided by 4K, 4 second EE to the third plus 1 divided by 1 second EE to the third plus 1 divided by 4 second EE to the third plus 1 divided by 400. And then hit my final parenthesis and equal, and note it gives us 200 ohms. The 2 combination formula was used when calculators didn't easily allow us to put in the entire equation. All right, now we're going to analyze our first parallel circuit. And we know that when things are in parallel, they share the same voltage. So we know that this is going to be 36 volts here and 36 volts across here. So we can go ahead and write those down, 36 volts, 36 volts. And we can apply Ohm's law to calculate the current in each one. So we do so. So 36 volts divided by 1.2K ohms gives us 30 milliamps. 36 volts divided by 1.8K ohms gives us 20 milliamps. So I'm going to go and take that information and draw it right here. So we know that we're going to have the total current coming in here. It's going to have 30 milliamps going up this branch and 20 milliamps going down this branch. Now we can simply say, using Kirchoff's current law, that 30 milliamps plus 20 milliamps should add up to the total current. So we could simply say this is going to be 50 milliamps. Now, let's go ahead and verify that. Let's go ahead and find the total resistance. So the total resistance is going to be equal to 1 over 1.2 k ohms plus 1 over 1.8 k ohms. And that gives us 720 ohms. And let's go ahead and apply Ohm's law. So if we have 36 volts and we divide that by 720 ohms, indeed that gives us 50 milliamps. So we are doing good. So we get 50 milliamps coming in here. Now if we take 50 milliamps and multiply that by our 36 volts, so I've got 36 volts times 50 milliamps. Let's go ahead and calculate that. So 36 volts times 50 milliamps gives us 1.8 watts. Here, to find the power here, 36 volts times 30 milliamps gives us 1.08 watts, and 36 volts times 20 milliamps equals 720 milliwatts. And 720 milli plus 1.08 watts adds up to 1.8 watts. Yay! Okay, so let's move on to circuit number 2. Okay, with circuit number 2, we now have 3 resistors, R1, R2, and R3. We can tell that these are in parallel because, see, they have alternate paths and they all share these 2 points, which basically says they all have 50 volts across them. So I can simply write down here 50 volts, 50 volts, and 50 volts. Woohoo! See, already got 3 answers down. Now, what law? Oh yeah, Ohm's law. And Ohm's law, if we apply it here, so we take 50 volts, divide it by our resistance of R1, which is 80 ohms, and that gives us 625 milliamps. If I take 50 volts and divide it by 100 ohms, that gives us 500 milliamps, and 50 volts divided by 400 ohms gives us 125 milliamps. So let's take a look at what we've got going on here in the circuit. So we said that we've got how much current going here? Well, we got 625. Now note, this point is the shared point, so it's just like the 2 of them going out of the same location. So 625, how much here? Well, we got 500 milliamps here, and then we have another 125 going out here. So what do all 3 of these add up to? Well, 625 plus 500 plus 125 adds up to 1.25 amps, or 1,250. Well, let's make sure that that equals what we think it should. So if I take my total resistance calculation, which is going to be 1 over 1 over 80 ohms plus 1 over 100 ohms plus 1 over, all of those 1 over, 400 ohms, we find that that equals 40 ohms. So if I take 50 volts divided by 40 ohms, that gives me 1.25 amps, which is exactly the current that we expected. Now, when we go ahead and calculate the power dissipated in each one, we take 50 volts times 625 milliamps, and that is going to equal 31.25 milliwatts. And 50 volts times 500 milliamps gives us 2.5 watts. Whoops, that should be watts there. And 50 volts times 125 milliamps gives us 6.25 watts. Now if we calculate our total power here, it's 50 volts times 1.25 amps, which gives us 62.5 watts, which 31.25 plus 25, my bad on that one, plus 6.25 watts adds up to 62.5 watts. That's what happens when you sometimes use the DNA calculator instead of the real one. Now, we will come down and do our next circuit here. Our next circuit, we have 3 resistors all in parallel. So we know that the voltage across each one is going to be 12 volts. So we got 12 volts here, 12 volts here, and 12 volts here. So let's go ahead and write those down. 12 volts, 12 volts, 12 volts. Okay, and we take 12 volts, divide that by 24 ohms, and that gives us 500 milliamps. If we take 12 volts here and divide it by, there's no value for that resistor. What are we going to do? Oh, well, we'll come back to that one. Okay, so here we've got 12 volts divided by 6 ohms, and that equals 2 amps. Okay, well, let's keep going. So 2 amps, so we've got 12 volts times 2 amps, which equals 24 watts. And, oh, can't do that one yet. Okay, well, we'll come over here. So 12 volts times 500 milliamps gives us 6 watts. Okay, oh, what? Hey, we have some information here. This says that our total power is equal to 48 watts. Well, we can find our total current, right? Because we can say, all right, 48 watts divided by 12 volts equals 4 amps. So that means that if I have 4 amps here and I have 500 milliamps here and I have 2 amps here, what is left to go down R2? Well, 4 minus 2 gives me 2, minus 0.5 gives me 1.5 amps. So, I now know this is 1.5 amps. I didn't even have to use Ohm's law for that. But I could find out what the resistance is simply by taking 12 volts. So our resistor for R2 could be found by taking our 12 volts divided by 1.5 amps, which gives us 8 ohms. Okay. And look, 12 volts divided by 8 ohms gives us 1.5 amps. Ooh, that worked out nicely. And we kind of knew if we had a 48 watts here, we could have also found it like this. We could have said, okay, 48 minus 24 minus 6 gives me 18 watts. And we could have said 18 watts divided by 12 volts is 1.5 amps. So we're doing really awesome on all of these. Everything is adding up just like it should. By golly, we haven't even found the total resistance yet. Now, we could do that a couple of ways. The first way, of course, is to apply Ohm's law. So we could say, all right, 12 volts divided by 4 amps equals 3 ohms. Or we could do it, now that we've found that R2 is 8 ohms, we could say 1 over 24 ohms plus 1 over 8 ohms plus 1 over 6 ohms gives us 3 ohms for our total resistance. So everything works out swimmingly. Now, one more concept to keep in mind when dealing with series and parallel circuits is often in reference to combining voltages and series aiding and series opposing. We know that when things are in series aiding, the plus is connected to a minus. Series opposing, either a plus is connected to a plus or a minus is connected to a minus. Now, if we have batteries, rarely do we ever connect those in series opposing. What we typically do is we put them together to either increase the voltage or increase the current. When we connect them in a series circuit like this, if I have 4 batteries that are 1.5 volts, 1.5 volts, 1.5 volts, and 1.5 volts, and each battery has the ability to supply 250 milliamps because we have one path, the maximum the current can go through that one path is 250 milliamps. Yet the voltage that it provides, since these are connected in series aiding, is the 4 of them added up together. Now, if we connect things in parallel, and by the way, when voltage sources or batteries are hooked up in parallel, they must be the same voltage. If one of them is less than the other, that causes problems. So when we connect things in parallel, note if we put the same batteries, the same 4 batteries in parallel, the total amount of voltage seen, instead of being 6 volts like in series, is just 1.5 volts. But the total current that they can supply is 1 amp because it's the 4 250s added together. Note, when combining things in series, you combine voltages. So you maximize voltage with batteries in series. You maximize the current when connected in parallel. Now, if you take those same 4 batteries and do various series parallel combinations, which I've chosen to do one here, if I take those same 4 batteries and I put 2 of them in series, and then in parallel with each other, note we get 3 volts as our overall voltage, but we now have a total of 500 milliamps that it can supply. So by connecting in series, we maximize voltage, parallel, maximize current, and if we do a series parallel combination, we can add both voltage and current. That's part of the reason why whenever you replace batteries, you must make sure that you always have good fresh batteries. If any one of them is not able to supply the same amount of current or the same voltage, it will cause drain, and they will act as loads rather than being voltage sources. Next, we will come back and talk about that wonderful combination of series and parallel combined.